بسم الله الرحمن الرحيم. Hello everybody, you are welcome. This is an exercise about mean value theorem and about sequences. Show that for all n in a natural number, we have 1 over n plus 1 is less than logarithm Neperian of n plus 1 minus logarithm of n less than 1 over n. Reduce that the sequence Sn, which is equal to 1 plus 1 half plus 1 over n, is divergent. Second question, show that for all n in n natural numbers, we have 1 over 2 square root of n plus 1 is less than the square root of n plus 1 minus the square root of n, which is less than 1 over 2 the square root of n. Deduce that the sequences un, which is equal to 1 over the square root of n times 1 plus 1 over square root of n plus dot plus 1 the square root of n is convergent. Here we will use the mean value theorem, for example, to answer all these questions, but we have other ways to carry on these questions. For the first, so let us consider, for the first question, let us consider the function f of x, which equal to ln x, and x belongs to n plus 1. N belongs to n, this means that n is different of 0. F is continuous on n plus 1. F is differentiable on n plus 1. Then by the theorem mean value theorem applied to f on the interval n plus 1, there exists a constant c which belongs to n plus 1, such that what? Such that f of x minus f of, such that f of n plus 1 minus f of n, this is equal to n plus 1 minus n times f prime on c. If we translate this into this precise function, we get ln n plus 1 minus ln n equal 1. F prime, this means 1 over c. Don't forget that c belongs to n plus 1. This means that since c belongs to n plus 1, this means that it is strictly less than 1 over n and strictly greater than 1 over n plus 1. So here we have this formula, which is true for all n greater than or equal to 1. Deduce that the sequence Sn is divergent. Actually, we use this double inequality. In this case, we use just the right one. This is true for all n in natural numbers. So let us consider ln k plus 1 minus ln k. This is less than or equal to 1 over k. If we take here the sum from k equal 1 to n, from this side we will take the sum from k equal 1 to n. Here we find Sn, and this is a telescopic sum. This means that this is equal to the last for this one, ln n plus 1, and the first for this one, which means minus ln 1, which is equal to 0. When n goes to plus infinity, this goes to plus infinity, and since this is less than this sum, which is the sequence, this means that it goes to plus infinity, which means that it is divergent sequence. How about the second question? For the second question, we will follow approximately the same way, but here we have a choice. We can choose this way and we can choose another way. For the question B, how we can show that this double inequality is true? We can once again use mean value theorem. Applied on what? Applied on n and n plus 1 once again, but the function in this case g of x, it is equal to the square root of x. Since n is greater than or equal to 1, this function is continuous on n plus 1, and it is differentiable on n plus 1. Applying mean value theorem, this gives us the right to say that there exists a c which belongs to n plus 1, such that what? Such that g of n plus 1 minus g of n, this is equal to n plus 1 minus n, which is 1, times the derivative. The derivative is this function. And since c belongs to n plus 1, this means that it's strictly less than 1, the square root of n, and it is strictly greater than 1 over 2, the square root of n plus 1. This is a way. Actually, we have a second way. We take just this formula. We have here n plus 1 minus n. We times by the conjugate. So if we times by the conjugate, we get n plus 1 plus n divided by n plus 1 plus n. From the numerator we get n plus 1 minus n, this means 1, and from the denominator we have n plus 1 plus the square root of n. This is strictly greater than 1 over 2 the square root of n plus 1, and is strictly less than 1 to the square root of n. So we have two ways to deal with this question. Deduce that un, which is equal to 1 over the square root of n times 1 plus 1 the square root of 2 plus 1 over the square root of n is convergent. The question honestly is a little bit confusing. Why? Because if you find this question like this, you will understand that we have a double inequality, so we will prove that this sequence is bounded. Then I tried actually to prove that it is monotonic. It's not monotonic. It's hardly appearing if it is monotonic or not. Honestly, I didn't find the way using this technique. Why? Because here we have an expression which is increasing and expression which is decreasing, so it's a little bit hard to find if it is monotonic or not. It is monotonic, but it's very hard to prove. I think that it can be monotonic, it can be increasing, but it is not obvious honestly. What is the way that I took? The way is the following technique. So we have actually two methods. We use this first. So we write what we can write. We can write the square root of k plus 1 minus the square root of k. This is less than, let's us take here 2. This is less than 1 the square root of k, and greater than 1 the square root of k plus 1. Now we will be interested to this side. If we take the sum from k equal 1 to n minus 1, we have here 2, the sum of the square root of k plus 1 minus the square root of k. This is less than the sum from k equal 1 to n minus 1 of the sum 1 over k. From this side we keep 2, the sum, so the first one and the last one, so we have n. We replace k by n minus 1, so we have the square root of n, and here we have the square root of 1. I mean this. This is less than the sum from 1 plus 1 over the square root of n minus 1. Since this is less than this chart, if we add plus 1 over the square root of n, it's still true. Then what we can do from this side, we have 2 the square root of n minus 2 less than 1 plus 1 the square root of n. If we divide by the square root of 2, we keep here 2 minus 2 the square root of n, and here we have the square root of n. This is un. Yes, this is un. So un is greater than 2 minus 2 over the square root of n. Now we will use this side. We will use this side. I will write this result here. So we have 2 minus 2 the square root of n is less than un. This is what we find here. Now we will use this side and we will sum. So we sum from k equal, actually we can start here, we can start from k equal to 0. We can do it in this side, but I will start from k equal to 1 until n minus 1. Once again, 1 the square root of k plus 1. This is less than telescopic method, the first for this and the last for this. We get 2 the square root of n. Here we start from k equal 1 to the square root of n minus 1, the square root of, we have k plus 1 until n minus 1, so we have 2 the square root of n minus what? Minus 1. Here we take 1 minus 1 from here, we have minus 2, so we take minus 1 from here to this side, and we divide by the square root of n. We get, I will do it, so we have 1 from this minus 1 plus, we start from k equal 1, so 1 the square root of 2 plus 1 the square root of n, the last one. This is less than 2 minus 1. I took minus 1 to this side. This is, if we divide it by the square root of n, we get over the square root of n, and here we have the square root of n. This is actually un. So un is less than 2 minus 1 over square root of n, and greater than 2 minus 2 the square root of n. When n goes to plus infinity, our sequence un goes to 2. So it is convergent. The question should be, it could be better if we ask calculate the limit using this, calculate the limit of the sequence. It will be more accurate, yeah. Here actually we have a second way. I will just give you the idea. We can do it slightly without using this inequality, but a sister of this double inequality, an inequality of its family. We can write that the square root of k is less than the square root of k plus the square root of k plus 1 divided by 2. And the square root of k is greater than the square root of k plus the square root of k minus 1 divided by 2. This is true for all k which belong to n. I mean 1, 2, 3, and so on. If we take the converse, what we will get? We will get this first. So 2 divided by the square root of k plus the square root of k plus 1, less than 1 the square root of k, less than this one, which is 2 divided by the square root of k plus the square root of k minus 1. From this side, this is actually equal to what? This actually is equal, this is equal to 2, the square root of k minus the square root k plus 1 minus the square root of k. This side, the same idea that we used before. And this one is equal to 2, the square root of k minus the square root of k minus 1. And here, if we take the sums, we will get approximately a squeeze result like that we used before. It's more simple, but we have to get this little idea. I think that I finished this video. Thank you for watching. See you next time, inshallah.